Hello to everyone. Welcome to the course on linear algebra and application. Today we are going to have 41st lecture of this course. Before going to the contents of this course for today's lecture, let us recall what we did in the previous lecture. In the previous lecture, we were trying to speak the convergence of iterative methods. There are three iterative methods as we have seen: Gauss-Jacobi method, Gauss-Seidel iteration method, successive or relaxation method. Every method has its own advantages and disadvantages. One method is faster compared to some other method and vice versa. Today we are going to learn some examples of these three methods. First and foremost example is Jacobi method for symmetric matrices. And if you see the first example, using Jacobi method, find all the eigenvalues and the corresponding eigenvectors of the matrix given in the 3 by 3 form. First row is 1 root 2 2, second row is root 2 3 root 1, third row is 2 root 2 1. The largest off diagonal element is A13 or A31. So that is off diagonal element. The other two elements, in this case 2 by 2 submatrix, are A11 is 1, A33 is 1. So if you write this, theta is equal to 1 by 2 times of tan inverse of 4 0. So it turns out to be pi over 4. And we can write this matrix S1 as 1 over root 2, 0, 1 over root 2, 0, 1, 0, 1 over root 2, 0, 1 over root 2. The first column gives you B1 is equal to S1 inverse AS1. That will be equivalent to 1 over root 2, 0, 1 over root 2, 0, 1, 0, 1 over root 2, 0, 1 over root 2. Multiplied with 1 root 2, 2. Root 2, 2, 3, root 1, 2, root 2, 1. And again multiplied with S1, which is 1 over root 2, 0, 1 over root 2, 0, 1, 0, 1 over root 2, 0, 1 over root 2. Which turns out to be 3, 2, 0, 2, 3, 0, 0, 0, minus 1. The largest off diagonal element in magnitude in B1 is A12 is equal to A21 is equal to 2. The other elements are 3 and A22 is equal to 3. Therefore, theta is equal to 1 by 2 times of tan inverse 4 0, which turns out to be pi over 4. and the matrix S2 is equal to 1 over root 2 minus 1 over root 2 0, 1 over root 2, 1 over root 2 0, 0, 0, 1. And second rotation will give you what we call B2, that is S2 inverse B1 S2, which turns out to be 5 0 0 0 1 0 0 0 minus 1. We have the matrix of eigenvector as S is equal to S1 S2. So that is 1 over root 2 0 1 over root 2 0 1 0 1 over root 2 0 1 over root 2 multiplied with 1 over root 2 minus 1 over root 2 0, 1 over root 2 1 over root 2 0 0 0 1, which will give you the matrix, that is 1 over 2 minus 1 over root 2 minus 1 over root 2, 1 over root 2 1 over root 2 0, 1 over 2 minus 1 over 2 1 over root 2. Therefore, the eigenvalues are lambda is equal to 5, 1, minus 1. And the corresponding eigenvectors are the columns of the matrix, columns of S. And if you look at second example, find all the eigenvalues of the matrix 3 by 3 matrix. 1 2 minus 1, 2 1 2, minus 1 2 1. Using the Jacobi method, till off diagonal elements in magnitude are less than 0.0005. The largest off diagonal element in magnitude is A12. Therefore, we will write it as tan of 2 theta is equal to 2A12 upon A11 minus A22. So, which turns out to be infinity, because something by 0 is infinity, or theta is equal to pi by 4. So, the S1 turns out to be 1 over root 2 minus 1 over root 2 0, 1 over root 2 1 over root 2 0 0 0 1. The first rotation gives you this matrix, that is B1 is equal to S1 inverse AS1, which turns out to be like this: 3 0 1 over root 2, 0 minus 1 3 over root 2, 1 over root 2 3 over root 2 1. And the largest off diagonal element in magnitude in B1 is A of 2 3. So therefore, you will have tan of 2 theta is equal to 2A23 upon A22 minus A33. So which will give you minus of 211320, or theta is equal to minus of 0.565143, and cos theta is equal to 0.844512, sin theta is equal to minus of 0.535537. So therefore, S2 you get as 100, 0 cos theta minus sin theta, 0 sin theta cos theta. And second rotation gives you B2 is equal to S2 inverse B1 S2, which will be in this form. The largest half diagonal element we want to is A13, that is this value out of the other than this main diagonal. Therefore, we will write tan 2 theta as 2 times of A13 upon A11 minus A33, which turns out to be 1.823969. So, cos of theta is equal to 0.860449. And S3 is equal to cos theta 0 minus sin theta 0 1 0 sin theta 0 cos theta. The third rotation gives you this matrix 3.353625 minus 0.325837 0.0001 minus of 0.325337 minus 2.345208 0.192952 0.5001 0.192952 1.991585. So the largest off diagonal element in magnitude in B13 is A12. Therefore, we will write it as tan of 2 theta is equal to 2 times of A12 upon A11 minus A22. So which ultimately turns out to be this value minus of 0.056929. So therefore, we will write it as cos theta is equal to 0.998380 and sin theta is equal to minus of 0.056898. So finally, you will end up with S4, that is cos theta minus sin theta 0, sin theta cos theta 0, 0 0 1. So the fourth rotation gives you this matrix. B4 is S4 inverse B3 S4. You get a value 0 and this value and this value. The largest off diagonal element in magnitude in B4 is A23. That is second row, third element. This value, that is 0.192639. So then we can compute this tan theta as tan of 2 theta is equal to this 2a3 upon 283 upon a22 minus a33. That is equal to minus of 0.088462. Or theta is equal to this value minus of 0.044.044116. So ultimately the cos theta will be 0.999027 and sin theta is minus of 0.044102. So we can write S5 as 100 0 sin cos theta minus sin theta 0 sin theta cos theta. So we'll write fifth rotation gives you this matrix B5. So look at this. This is the A11, A22, A33. So the largest off diagonal element in magnitude in B5 is A13. So therefore we will write it as tan of 2 theta is equal to 2 times of A13 upon A11 minus A33. So which will be equivalent to minus of 0.015987. Or you can write theta is equal to minus of 0.00792. So you will have S6 is equal to cos theta minus sin theta 0 0 1 0 sin theta 0 cos of theta. So sixth rotation gives you this matrix B6, that is B of 6 is equal to S6 minus B5 S6. So you get a matrix like this. Hence the approximate eigenvalues are 3.372283 minus of 2.372281 and 1.999998. So if you write this lambda 1 plus square root of 33 upon 2, which will give you these values. Given the method for symmetric matrices, the third example is transform this matrix 3 by 3 matrix to tridiagonal form by using the Givens method as we did it in the last before lecture. Using the exact arithmetic, we will write it as perform the orthogonal rotation with respect to A22, A23, A32, A33 and submatrix you get like this. So tan of theta is equal to A13 upon A12, which will be equivalent to 3 upon 2. So cos of theta is equal to 2 over square root of 13, sin of theta is equal to 3 over square root of 13. So you get a matrix B 1 0 0 0 2 over 13 3 over 13 0 minus 3 over 13 2 over 13 multiplied with 1 2 3 2 1 minus 1 3 minus 1 1 and multiplied with S inverse, that is 1 0 0 0 2 over 13 minus 3 over 13 0 3 over 13 2 over 13, and which will give you 1 root 13 0 root 13 1 over 13 5 over 13 0 5 over 13 2 over 25 upon 13, which is the required element in the which is the diagonal form. If you look at this is the main diagonal, subdiagonal, this is 0 and this is 0. Let us look at into the fourth example. Let us transform this matrix, that is 3 by 3 matrix, to a tridiagonal form by using the Givens method. Obtain the intervals of unit length, each containing one eigenvalue of A. Find the largest positive eigenvalue corresponding to 2 decimal places. Let's say using the Newton-Raphson method we are using it. So you get as the orthogonal rotation when you use it with respect to A22, A23, A32, A33. So you get a matrix like this. Tan 2 theta is A13 upon A12, which is equal to 2, and cos theta is 1 over square root of 5 and sin theta is 2 over square root of 5. So if you multiply that, you get ultimately this matrix. So again you see here, this is a banded matrix, tridiagonal, and this is 0 and this is 0. So the term sequence, what it tells is, the first one F0 is 0, F1 is lambda minus 1, F2 is lambda minus 2.6 times of lambda minus 1, which is a square root, and F3 will be a cube root. So we will find out that F3 of minus 3 is 0, F of minus 1 is 8, and all these things we compute. Therefore, one eigenvalue of is minus 3 and the other eigenvalues are in the interval are minus 1, 0, 6, 7. So starting with lambda is equal to 6.5 as initial approximation, now we will arrive this method. That is lambda of k plus 1 is equal to lambda k minus f3 times of lambda k upon f3 times of lambda k, and assuming that f3 prime of lambda k is free from 0. Therefore, the largest positive eigenvalue correct to 2 decimal places is 6.46. So today in this lecture what we learned is, we learned some examples related to the Gaussian convergence and some given method, how these methods could be handled for a best approximation using the eigenvalues and eigenfunctions. Thank you very much for listening to my lecture today. Thank you once again.